First, we have Alex Schwing. Alex Schwing is our associate professor in the Department of Electrical and Computer Engineering and Computer Science. He's an expert in computer vision and machine learning. He publishes extensively in highly regarded computer vision and machine learning international conferences. Without further ado, here's Alex.
Thanks a lot for this nice introduction. We got to find some title. So I talk about what I call aBridging diffusion models. Essentially what I try to do is present a slightly different view on diffusion models. And I hope by the end of this talk, I can convince you that diffusion models are nothing else but a fancy version of k-means. So we'll see whether we get there. I also try to make this a bit more interactive. I apologize for everyone watching online. I can't see your interactions. But I try to ask some questions during the talk. No need for microphones. Just shout at me. I hope I can pick it up. All right. With that being said, some of the results I will be showing are from this set of amazing students and collaborators. They're really the ones that do all the work. They deserve all the credit. And I'm hoping you recognize some of them here. All right, brief introduction, what am I generally interested in? I'm sure everyone here is aware of the fact that computer vision and machine learning have been remarkably successful in the last couple of years, maybe in the last 10 years. And I would argue that models which what I call analyze work very well. So what do I mean by analyze is things like image classification, object detection, but also semantic segmentation. You see a result of one of our methods, mask-former, at the bottom. And video object segmentation. What these methods typically do is they take an input and then you ought to predict something. So you essentially have all the data available. Now, but I would also argue that analyzing, just predicting or reasoning based on what you observe is not sufficient anymore. We are interested in many more challenging applications like novel view synthesis in AR or VR applications. And there are two of my students. And you want to not only infer based on what you see, but you want to observe or you want to infer about things that are behind where they're standing. And you want to do that from different viewpoints, for instance. Or you want to do forecasting in autonomous systems, right? You observe the image shown at the top, and you want to reason about what is the semantic segmentation going to look like a few seconds from now. Or high-level image editing. You're given a 2D snapshot, and you want to segment it, but in 3D. Now, all this requires you to look beyond what is actually visible. So we need to look behind the scene, which is usually the title that I use, but doesn't fit TBD. Anyway, to do that, you need a whole bunch of systems to play nicely together. First of all, you need to do holistic object understanding. You need accurate probabilistic models. You need detailed forecasting abilities and fine-grained interaction models. All these are things that I'm personally interested in and students that I work with are excited about. I'll not have the time to talk about many of these things. I'll just briefly show some highlights of the works that we're doing here. And I primarily focus on this generative modeling part, given that this is a generative AI workshop. Skip through this part. Generative modeling, here we go. Many people have talked about it. I missed early talks because of flight issues, but I haven't seen anyone really carefully defining what this are, what generative modeling really is. So I tried to really give a very basic background and hopefully guide everyone along my thinking. So what's the goal of generative modeling? Essentially, we want to learn a model that can generate new data that looks like a given set of data points. So if you break this down into the very basics, we're given the green points that you see on the right-hand side here. That's our data set. Now we want to generate new data points. And I'm sure we all agree that the blue dot here is probably much more likely to come from this data set than the red dot. Now, one thing I also want to emphasize is that we're given data points, but never, ever the underlying distribution. So all we're given is these green dots. Now, briefly jumping into that part here, generative versus discriminative. Oftentimes, I'm not sure we should actually differentiate them, but for the sake of doing it, let me just try. For generative, we want to generate new data points. We want to hypothesize multiple solutions. And probably according to my opinion, most crucial difference is that we want to train probabilistic models that don't just average results. Now, what do I mean by that? By that, I mean if you're giving it the same input, the same condition, then these generative models can map to multiple differing outputs. Say, same text goes in, you might get different images at the output. And the way, according to my opinion, generative models achieve this is by having additionally some noise or some latent variable that's used as an additional input. If you don't have that noise or that latent variable, what often happens is some sort of averaging. To make it concrete, consider, say, a grayscale image of myself that goes in, and you want a system to predict a color image. If you take images of yourself wearing a blue shirt and a red shirt, and you train a discriminative model, then you will get at the output some sort of purple shirt, but not a system that can generate both of those images. Now, people often say that generative modeling is harder and requires more training data. Whether or not that's true, let's leave it at that, maybe. There's a ton of different types of generative models. Maybe I'll start with a question here. Which generative models do you know? What comes to your mind? GANs is one. Yes, great example. Other examples? Diffusion, yes, obviously. We have heard about that. More examples?
Kernel density.
Great example, yes. Others? Students here, yes, please. What was it? GPT. I'll personally be careful with that. We can talk maybe offline why I'm a bit more careful with that. But let's say yes. Variation autoencoders, yes. All these k-means, yes, exactly. I was about to say, all these fancy ones. Where are the simple ones? Other simple ones. Flow-based models, yes, I'll have a slide on that. One more. Very basic. PCFGs. Yes, very fancy models. I'll not get into those.
Memorization and then.
Yes, that's right. I like that one.
Hidden Markov models.
Oh, yes, good one. I love hidden Markov models. We could have an entire lecture on that. Not go there today. Good. Even more basic, right? Single Gaussian. It's a generative model. Gaussian mixture models, k-means we heard. And essentially, what I'm trying to do today is to convince you that, well, obviously, Gaussian mixture model is an extension of a single Gaussian. K-means is a special case of a Gaussian mixture model. And variational autoencoder, which is just a fancy version of a Gaussian mixture model. And a diffusion model is just a hierarchical variational autoencoder. And if you believe in that, well, then I already proved my point that the diffusion model is just a fancy version of k-means. And all this SDEs and ODEs, great to have, good underlying theory, but to really understand them, you probably don't exactly need it. Or let me put it this way, to use them, you don't really need all that. Yes, there's autoregressive methods. Someone mentioned GPT earlier, a fancy version of an autoregressive method. Generative adversarial networks were mentioned. Have a brief slide on that too. Okay, great. So let's jump into this. Here's our single Gaussian. What are the parameters of a single Gaussian? Mean and variance, yes, exactly. So we're given the green points. I showed you those earlier today. You want to estimate mean and variance. Why is the mean and variance of the distribution highlighted in blue concentric circles better than the one in red? Exactly. The likelihood is higher. What do, right? You look at the isolines here, look at the points, you evaluate for every single point what's the likelihood of the green points under the distribution illustrated by the blue concentric circles. Well, it's very low because the green points are far off from the center. In contrast, they're much closer to the blue one. So if we get to choose between the distribution illustrated by blue concentric circles versus the one in red, well, we would obviously pick the blue. Now you can do this example hundreds of times, give yourself tons of distributions, and you would always pick the blue one. Now, how do we compute the mean and the variance? How do we do this maximum likelihood estimation, right? We want to find the distribution that has the highest likelihood. How do we do that for a single Gaussian? Everyone forgot about the single Gaussians already? How do we maximize the likelihood? Closed form, yes, exactly. Closed form, it's trivial. Take your data and average it, compute the covariance, you're done. That's it. Now, why is a single Gaussian great to use? Well, exactly because of that reason, right? It's trivial to use. You have everything right there. It's quick to compute. You can even compute it in a streaming-based manner, done. However, I give you tons of images and want you to learn to generate new images. Would you use a single Gaussian? Probably not. And if you would tell someone that you're going to use a single Gaussian, they might question your sanity. Anyway, we talked about all this right now. Parameters, mean and standard deviation, maximum likelihood estimation, closed form. Trivial are the benefits. Shortcoming, well, it's not very flexible. OK, great. If it's not very flexible, let's do the next best thing. What's the next best thing? Well, maybe do a jump to k-means first, but we can also do Gaussian mixture models. What are the parameters of k-means? Right, I already heard it somewhere, centroids. Yes, exactly. We'll try to get these centroids. How do you get those centroids? Expectation maximization, Lloyd's algorithm, you name it, alternating optimization, all the same thing. Exactly. What are the benefits of k-means? Well, it's still very easy to do. What are the shortcomings? Same as before. It doesn't generalize very well. Here we go. Parameter centroids, maximum likelihood estimation, alternating optimization, analytic solutions in each step. Important to highlight. Parameter estimation is easy. We have a lot of theory on it. Shortcomings, centroids are not very good data representations or very flexible. Let's put it this way. Gaussian mixture model. If you go to high dimensions, you just run into problems. For 2D, yes, it's good. It's fine. But for high dimensions, I think you just need too many centroids to properly capture your data. Yes, you can take a lot of centroids, that's sure. But then we're back to Greg's point. I just keep the entire data around. Sure, it doesn't compress things very well. Good. K-means, great. Let's generalize it. One of the issues with K-means, you just have your centroids. You don't really have a distribution around them. Let's make it a bit more complicated. Well, the next best thing, Gaussian mixture models. What are the parameters of Gaussian mixture models? That's right. Mean, variances, and weights. That's it. Standard. OK, great. Fine. How do we get the maximum likelihood solution? I already had that earlier. Expectation maximization is the common thing. It's just alternating optimization. Fine. Benefits, more flexible than a single Gaussian. Shortcomings, well, decently flexible, but maybe not quite there yet. I think this time I have 2 slides on this. They essentially say exactly what I just talked about. And here are the benefits, more flexible, shortcomings, maybe still not all that flexible either. OK, now the next big jump, maybe a slightly bigger jump. For Gaussians, we do expectation maximization. Expectation maximization essentially means there is 2 distributions that you're trying to work with. One is your distribution of given a data point, what cluster do you assign it to? Q of C given X, that's the posterior. And the second one is if you know what cluster you assign the data point to, what is the likelihood? That's P of X given Z. These are essentially the 2 distributions that you're working with. And you have explicit forms. Great, all fine. But now let's make one more step. Right? Let's look at variation autoencoders. Here's the first picture. that I find somewhere on the internet, there's a Q of z given x, and there's a P of x given c. Now, what's different here compared to a Gaussian mixture model? The latent is continuous, yes, that's one important point. What else is different? If you use an autoencoder, what else do you typically use? Very practical. You probably put some deep nets there, right? You don't have to. No one tells you that you have to, but oftentimes you do, particularly if you care about images. And that's really it. Yes, you can also have an autoencoder there. For sake of this discussion, let's just assume there's a variation autoencoder, but then you work with the same distributions. So in essence, I could make the argument that a variational autoencoder is just a Gaussian mixture model on deep nets or on steroids. Parameters of the model, you learn some deep net mappings. We then call them encoder and decoder instead of, and maybe I shouldn't write instead of distributions, because essentially they are distributions and they are still the posterior and the conditional. And maybe they are not in this discrete kind of handcrafted space, but in some continuous space, as Greg pointed out. Maximum likelihood estimation. OK, great. This is one of the issues coming up now where we have deep nets. Things are not nice and necessarily convex anymore. So we have some form of iterative optimization, very similar to an expectation maximization algorithm. There is no analytic solution anymore whatsoever compared to Gaussian mixture models. So it's computationally more demanding, which kind of makes the point that I showed on one of the earlier slides. Generative models are a bit harder. And here we go. Benefits for variational autoencoders, I would argue, still very well understood probabilistic models, easy to optimize, sampling via single-step deep net forward pass of a noise or latent variable. Remember, this is what I mentioned. This is Z, this latent variable is essentially the noise that allows these generative models to disentangle multiple solutions for the same conditioning input. Shortcomings, often less competitive or only competitive with significant manual effort. There's a few examples of these manual efforts that have been put into those original variational autoencoders, and they allow you to sample very realistically looking images of faces for now. OK, great. We are at variational autoencoders. Here we go. Next big step, diffusion models. We have heard a lot about them. How do I get from variational autoencoders to diffusion models? Well, before we answer that question, let's maybe talk about what exactly are diffusion models. What are the parameters that you train in a diffusion model, if you train a diffusion model? I'm sure all the students here have trained diffusion models. They probably know that better than I do. What are the parameters? The denoising network, exactly, the denoising unit. That's what you train. Now, here we go. Parameters, it's a single deep net that operates on some noisy data. That's the latent variable. It also takes a time step as input. And then you start with something very noisy, and you're trying to denoise it over time. And obviously, your denoising unit's goal is to predict something slightly less noisy. Maximum likelihood estimation, very, very similar. Don't have to go through it. Now, the interesting thing is you can actually write this out as a sequence of ki divergences over these time steps. And I'll skip all the math on these slides. Not really important. Let's focus on the intuition here. But what you end up getting is essentially a hierarchical variational autoencoder. And a hierarchical variation autoencoder with time as the index. Now, you'll have to make a few more simplifications because a hierarchical variation autoencoder is actually more general than a diffusion model. And some assumptions that you need to make, I believe I have them on a later slide, are on using Gaussians as distributions for your noising process, meaning for your encoder, as opposed to using standard distributions. But I would also make the argument, if you want to go forward and improve a diffusion model, that's probably an interesting intuition to have and to try to generalize along this direction of distributions. I'm saying that without having tried it. I'll encourage someone to try it. Let me know what happens. Benefits, quality matches state of the art, clear probabilistic interpretation, reasonably stable to train compared to some other methods that I talk about in a bit. Shortcomings, sampling is now computationally demanding because you have to go through this entire denoising process from time step capital T all the way to 0, which means you have to run your denoising unit a certain number of times, although people are trying to reduce that. Training is possibly data hungry. Great. Why do we see these compelling results? What is one of the main intuitions? Well, if we start with variational autoencoders and we improved upon variational autoencoders, in what way do they improve upon the variational autoencoders? Well, they improve upon them via this time index. So this time index does something to them that an original variational autoencoder doesn't have. So what does it do? Well, instead of directly modeling the data via this single forward pass from noise, so instead of going from noise straight to your data, which is from a Gaussian distribution to a very and highly complicated distribution, what you do is you're trying to essentially gradually improve the noise towards the data distribution one step at a time. And these individual single step changes, I'd argue, are easier to model via simple distributions like a Gaussian than trying to model the entire step all at once. And there's a nice picture in some paper, I forgot the reference, which essentially illustrates that. On the left-hand side here, that's your final distribution, bimodal, 2 Gaussians. On the right-hand side, there is a single Gaussian. And on the x-axis is the time step. So that's the time axis. And you can see you start from a single Gaussian and gradually morph it into this, in this case, still very simple bimodal distribution. Yes, you could probably easily fit the Gaussian mixture model to that. But for the sake of it, let's use the diffusion model. OK, good. That was the main message of the talk. Now everyone can go sleep. Joking. Few more things. Yes, I already made that point. Diffusion models are hierarchical variation autoencoders with 3 simplifications, and you can actually literally make this formula. Like I can write out the diffusion model, KL divergences, make these 3 simplifications, and I'll end up at eventually a variational autoencoder, and using the discussion that I made before, making further simplifications, we'll eventually end up with k-means or a Gaussian mixture model. I'll not go into the details. If you have any questions on this, if you want to see the formal derivations, reach out. I'm very happy to point you to papers and literature which makes all these points. All right, a few more things that I mentioned before. Someone earlier mentioned GPT. It's essentially an autoregressive method. It's often used for modeling sequence data. LLMs is what everyone uses these days. It decomposes a joint distribution over a sequence of tokens into a product of individual conditioners. Obviously has certain benefits. The conditions are sometimes easier to model than modeling the entire joint. Shortcoming, inference is sequential in the tokens. Got to deal with that. Not everything is for free. Generative adversarial networks was, I believe, the first one that was mentioned when I asked about different generative models. Parameters, in this case, 2 deep nets. We call them a generator and a discriminator. It's not really a probabilistic model. Instead, we're trying to directly learn to sample, again, by mapping this noise or latent variable to data. That's done by the generator, and then differentiating the generated data from real-world data via the discriminator. It's an interesting model. I haven't managed to put it into that context or that picture that I depicted beforehand. If someone knows how to do it, let me know. For now, I treat this as a separate instance of a generative model. Very interesting. And it also produces state-of-the-art results, I would argue. Sampling is efficient via a single deep net forward pass through the generator. Shortcomings, training is non-trivial, particularly if you're working with data that no one else has worked with before. Yes, if you care about images, there's plenty of great GANs out there. But if you're trying to go into a different domain, you've got to fiddle a bit with the hyperparameters. And these results are from StyGAN version 3. Someone else mentioned flows before. Here is my one slide on flows. Great work. They are invertible, so you can easily go from the latent space to the data space and back. But that might also limit their expressiveness, so I not talk much more about these ones. And energy-based models had an interesting discussion earlier today about graphical models. I'd love for them to come back. Personally, I don't believe it. Anyway, benefit, they are interpretable. All right. This was my short excursion into generative models and trying to link them together. And I should check how much time do I have left. 50 minutes. OK, perfect. What I want to do next is talk about a couple of works that my students and collaborators did using two of these methods. One of them, obviously, diffusion models. We can't resist either. And the other one, generative adversarial nets. And then I tried to conclude, and I tried to do all that in 10 minutes, even though I probably do injustice to both of these works. All right. Here we're trying to model 3D shape completion, reconstruction, and generation with one single diffusion network. So the goal is to generate a 3D shape given as input a partial shape. So for instance, you're given the parts highlighted in red, and you want to complete them and generate whatever is the complete object. And you get diverse results like the ones that you see on the right-hand side. And note the point that I made before, same conditioning input, different output. That's exactly because of these latent variables or noise variables that are used in generative models. Or suppose I give you an image, and then you want to generate the 3D reconstruction from there. Or I give you text. I want you to generate a rocking chair. You get outputs like this one. And some of them are maybe more rocking than others. Or any combination of the above, which is you might have, say, an image as input and a text as input, both of them, a chair with arms plus this image. And then I define the conditioning strength, and I get outputs like the ones illustrated here. Some are more faithful to the image, some are more faithful to a chair with arms, and others try to be faithful to both and maybe fail at both. Anyway, how do we do that? By now, it's probably fairly boring to go through this. If I tell you about latent diffusion models, then everything is being said. Essentially, we are trying to learn a generative model over 3D representation. So we assume we are given 3D training data. Obvious question is, what is the right representation for 3D data? You can use any number of them. You can use a mesh. People have done that. It's sparse, which is great, but it's hard to capture global structure. You can use voxels, which are great because you can easily model correlations between neighboring voxels, but they are high dimensional and maybe not really memory efficient. You can use signed distance functions. They are also high dimensional. They have a global structure somewhat encoded in them too. And I'm sure there's many more that you could use. We primarily went with the signed distance functions, hence the name SDiffusion. How do we deal with the high dimensionality? As probably at this point in time everyone else does too, project them into a latent space, formulate your diffusion in the latent space. That's it. I believe that's what this says, yes. And you can do some math on it and check. This is really more memory efficient than if you wouldn't use that. Good, somehow this works better. Again, I already told you how this actually works. You first train an encoder and a decoder on your 3D data. Fairly standard, use an autoencoder or a variational autoencoder for that. I already gave you the background on how to do it, how in quotation marks. So that means you then can essentially map your high dimensional data into a lower dimensional space. Let's call that lower dimensional space Z, and we attach the name, it's a latent space to it. Okay, great, fine. Now we take another generative model, namely a diffusion model. We run it in that latent space. Here is a picture that people often use. You're trying to essentially call this ZT, and then you're denoising it back to C. So you have the forward diffusion process, you have the backward diffusion process via your denoising network, all fairly standard. You have attention, and you condition it on different inputs or encoded versions of the input, and this is it. Anything else I should say about this? Probably not. And yes, you can condition on multiple things by having a network that kind of mixes these inputs together. How well does, oh yes, and if you want to do texturing, people have done score distillation. Yes, we tried that too, works reasonably well. I'm not going into the details of this in the interest of time. Instead, let me show you a couple of results. Shape completion, I already showed you some. Here is some input highlighted in blue, and the missing part is highlighted in red. And then we'll kind of complete that, right? This input, okay, we get something that looks more like tables or chairs, probably because the input in the data set is more likely a table or a chair. Here are some results of videos, rotating it around. Looks like fairly realistic 3D shapes, albeit somewhat simplistic, yes. Here we go, some more results and comparisons to other works back at the time when we did this. CVPR 23, not that long ago. Feels like these results are so outdated. Anyway, some more results. I skipped through this. This is text-guided shape generation, a chair with 5 legs. Yes, you'll get chairs with 5 legs. A somewhat circular chair, it does look somewhat circular, or a round table with 2 surfaces. Yeah, most of them, actually, yeah, pretty much all of them have 2 surfaces. And I could go on and on. In the interest of time, let me skip through some of these results. Here's just more of these with images. Here is conditioning on multiple inputs, an egg round shape, more weight to the right-hand side, more weight on the image to the bottom, and you'll get images that look more faithful towards either of these inputs. Here are some results with partial input given here in the top right, and then the images that it generates while trying to be faithful to either the image or the prompt or both, and considering as the given shape as input. Some work on texturing as well. I'll skip through those because I didn't really explain how we do that. And summarize that particular work. As diffusion, it's a conditional shape generation method. It uses cross-attention, classifier-free guidance, and texturing is done by training a neural radiance field. I know there's a lot of jargon here. Ask me specifically about individual terms if you're interested in that. I do want to spend, I believe, the last 5 minutes on this second work, which is now not using diffusion models, but now using generative adversarial nets, where we're trying to go one step beyond. Right? This first work, what we did is we essentially got 3D shapes, and we tried to learn a latent space of 3D shapes, and then reconstruct based on certain inputs. Now, we want to go one step further, right? And I kind of hinted at that with that seeing the unseen or seeing beyond what is directly visible. So we're only given input images, but we want to kind of infer the 3D shape or 3D information from only given input images. And the specific work I'm going to talk about is on generative multiplane images, making a 2D GAN 3D aware. This is work by great collaborators, and we really try to understand what are the minimal number of changes that you need to make in order to get 3D structure out of only 2D images. And this is, yes, 3D aware generation. Let me emphasize that again. Given 2D images as input, like the one, similar to those ones, we want to learn and this is important, a few consistent 3D representation of the data. And what I mean by few consistent is that you can essentially move around your camera, and there is no flickering or the the object is essentially the same that you'd look at, which is different from many prior works, that when you look at the result from different viewpoints, you will get clear artifacts and changes in the results, which, if you're interested in faces, is obviously disturbing, for instance. And yes, there's a lot of related work on that topic, amazing work. However, often not view consistent. That's what I just alluded to. And they sometimes make interesting choices on the representations that they work on, for instance, operating on individual points, or they take existing GAN structures and modify them entirely. Yes, they get great results, but what wasn't satisfying to us was, why did they actually work? Or what are the key ingredients that made these things work? Hence, the question of what is really needed to make, say, a 2D GAN 3D aware? What are the minimal number of changes that we need to make in order to get there? And the answer, I'll give you the answer first, and then I'll tell you a bit more about how. The answer is essentially use a very simple geometric structure, right? If you want to predict an image at the output, you somehow need to know something about the image generation process from 3D to 2D. And that's really the inductive bias that you're going to use here. And we use something extremely simple, which is a multiplane image. And without that, it unfortunately doesn't work. What you also need is you need to tell the discriminator in a GAN something about the geometry or where the image came from or what position the camera was placed at. And if you take these two things and modify an existing GAN in that way, you can extract 3D geometry out of just 2D images that are given to you. Okay, a bit more information about how we do that. An explicit model store information in planes, and each plane is an RGBA image. You can see that here on the right-hand side. Right, a multiplane image is essentially taking an image and decomposing it into different layers, or conversely, just having some information in 3D on certain layers and then trying to back project it down to the image. And the rendering is essentially exactly that. You apply some perspective transformation to every one of your planes and then apply some alpha composition on it. We did not propose that. That has already been done before we did. There is one reference here at the bottom right. They were not the first ones either. Here is essentially the overview. If you use a standard GAN, you start with, say, style GAN. You get an RGB image. That's your GAN. Now, there's a couple of things that you need to add to it. I alluded to that first. One is this alpha branch. That's essentially our 3D structure. In addition to the images, we're also predicting in the depth direction where should certain parts of the image go. That allows you to then produce this multiplane image. You then take this multiplane image, put it into a renderer. The renderer is very simple, as I just explained, right? Just move your planes according to the camera position, do alpha composition, and you get an image from a different perspective. And then you take your discriminator and you also put the pose in there. That is it. Yes, you can put shading in there too, not strictly required, but it does improve the results a bit and have some results on that too. In the interest of time, I skipped the alpha branch, very similar to if you're familiar with style GAN. It's essentially the same thing, except for applying it to multiple planes and conditioning on the depth. As I said before, you get the image, you get the depth. You can then take your image and decompose it according to depth. Nothing fancy happening there. And rendering is obviously fully differentiable, which you need to have, otherwise you can't backprop from the discriminator all the way down to your style GAN. The discriminator, I also mentioned that before. You need to condition it on pose. We do that in a very simple way, as opposed to using a classic discriminator that just takes an input image as input. We'll have that as well, but we'll multiply it with a transformed version of your pose as input that gets you your scalar at the output. Done. These are the two necessary components. I already mentioned that before. And here are some results to drive home the point that I just made. So if you just use style GAN, or you just predict 32 planes, you don't get any form of depth. In fact, there is no depth there. Doesn't really work. B is, yeah, that's the point B here. There's just no depth at all. C is if you use discriminator post-conditioning. You get a bit of depth, but not quite. D, where was D, is, we just condition the depth in the generator on we just provide depth in the generator on the alpha planes. It doesn't work either. Yes, somewhat, but not quite. And as soon as you put both of them together, all of a sudden, things start to make a lot more sense, and you'll start to get to see much more geometric structure coming in there. And I already made the point shading, that's the last one, F, where you can fix some of the strange-looking bumps, say, in the forehead by shading, which is obviously because whether, if the surface is convex or concave doesn't really matter, strictly speaking, for rendering, but shading will allow you to disentangle these factors. And yes, you can use more planes, and you get maybe slightly higher quality results, particularly if you move to the edges of the camera locations. Obviously, if you move too far, no matter how many planes you use, at some point in time you will be out. So you couldn't move, say, 90 degrees, which is one shortcoming of this particular representation. However, I would also make the point that you don't necessarily need to stick to that representation. You can probably use another one, and you might be able to address that issue. Last few points. This is very efficient to do compared to many of the prior works. I think some of these prior works need considerable amounts of GPU time and considerable amounts of rendering time. GMPIs are ridiculously efficient. You get frame rates, FPS, in the range of the hundreds. No problem, which is particularly important if you want to run this on some devices. All right, I should also make the point, this is provably few consistent. Obviously, there is no transformation after rendering. And you can see that this is a competitor, e.g. 3D. If you pay attention to the fur, once I start the video, you'll see a lot of flickering versus there is no flickering whatsoever on the fur on the right-hand side. And I'm hoping this comes across on this particular screen. You can see the flickering of the fur here, no flickering of any fur whatsoever. All right, summarizing, and then I wrap up. It's a GMPI extracted 3D given only 2D images. It's a depth conditioned MPI-based generator that is needed, and post-conditioned discriminator, and shading helps. You don't need to use it, though. Concluding overall, I think generative models have come a long way from k-means all the way to diffusion models. I'm sure it's not the end. I gave you one possible direction on how to generalize them. Looking forward to seeing someone do it. One other interesting question is how much inductive biases are really needed if you want to extract more information from data that doesn't provide this type of information. For instance, if you want to get 3D from 2D images, which is something that I'm personally very interested in. With that, I thank all the collaborators, sponsors that made all this possible. If you have any questions, happy to answer them now, later, or at any point in time, please feel free to reach out. Thank you very much.